All right, new unit here. So you notice on your note organizers it says kinematics, okay? That's a fancy way of saying we're talking about things that move, okay? We're talking about motion, we're talking about speed, we're talking about cars driving, okay? One of the reasons I like physics is because you can apply it to just so many things, all right? Think about everything that moves, all right? That's what we're going to be talking about. So we've already studied these 4 words in this class, okay? Where did we study distance? Wavelength. That's exactly right. Okay, we've already studied that. Okay, time we studied with period and frequency. Speed and velocity, we did the wave speed equation. Okay? Now the reason why I like to start you guys with waves is because check out these 4 words. Waves, we don't have to involve any of this. Acceleration. Okay, that opens a whole nother can of worms. Okay? You should know a little bit about acceleration though, because we read about it, right? Did we read about it?
Yeah.
Note organizer, you should know what these things are walking into class right now because you guys did your homework. Okay? Alright, so we're going to study all these things. Okay, just kind of a conversation starter here. Alright, what's going on in this picture? Is this a good situation to be in? Okay, we got a parking ticket situation going on. You know what, I should change this. I should get Ron in a picture. I'm going to change that PowerPoint slide. Okay, so do we got any motion going on here? Would this be a moving violation on your insurance points? No. Okay, however, is the car moving is kind of a weird question. Okay, here's what we have to ask ourselves. Moving relative to what? Motion is relative. Okay? Moving relative to the park or the officer, not moving. Okay? However, now is the car moving?
Yeah.
Very quickly. Now is the car moving?
Extremely quickly.
Yes, okay, it's going around the center of the galaxy. The car's like right there. All right, so motion is relative, or that's going to come up when we're talking about this stuff. All right, now most of the stuff we're going to discuss was not necessarily first thought of by Galileo. Okay, it wasn't the first one to think about this stuff, but he was kind of the first one to be accepted by the scientific community and write it all down. Okay? And the same year that Galileo died, Newton was born. You guys have heard of Isaac Newton. You've studied it in other classes. Most of the things we're going to talk about for this entire class are Galileo and Newton stuff. Okay? And within that, we're going to really be only studying 3 things in this class to start. Okay? We'll get into electricity and some other crazy stuff as well. But we're going to be studying mechanics in physics. Okay? Length, mass, and time. All right? So pretty easy, right? We're only studying 3 things. Okay, there's a lot of depth to this, though. Most of the questions I asked you this year are going to be related to this. All right, which sounds kind of crazy, only 3 things, but there's a lot of depth, like I said. Okay, we know this, we know what we need to measure things in, or sorry, not measure things in, but convert things to if we are going to do any calculations. Okay, and here's where our new terms start. All right, so in our notes there, distance, okay, let's put down a definition, total path length. Okay, just total path length. And so an example, we got a road on the screen. Let's say we drive from here to here. Okay, what's this? You guys know this place? You guys like this place. You can't see it, Mr. Nick. Okay, that's Powderhorn. All right, this is the Mesa. Okay. All right, switchbacks right here, it gets steep. Okay, this is Mesa Lakes. All right, we've all pretty much been to either Mesa Lakes or Powderhorn. Okay, so if you Look at your odometer, it will give you a distance measurement. It will give you a total path length. Okay? All right. Now the symbol or the abbreviation, what should we shorten distance to? Not a trick question. How about just D? Okay, now some of you said miles, that's a unit, okay, but it is not the unit. Okay, unit is meters. Okay, now we probably knew that. Let's talk about displacement. Okay, displacement would be that, all right? Now that is a tough path to travel, okay? You might hear as the crow flies. It's not even that. It's more like as the laser points, as the laser beam shines, okay? It's the straight line path. All right, now we're going to define it in our notes as change in position. Change in position. Okay, Henry, you getting the board here too? Okay, so change in position, displacement, we're going to abbreviate delta x. What's delta mean? Change in. Change, all right. X I like to think of as x marks the spot. Okay, x is position. Okay, so my arrow that I have on the board that looks like that, it's kind of like this is x initial, and this is x final. Okay, little i's and f's we will use for initial and final in here. So a delta is always a final minus initial. Okay, this is that. Okay, now it's still a length. Now we've studied distance, wavelength, and displacement. Okay, they're all measured in meters. That's the unit that we need. We might measure them in miles, but then we'll need to go to meters. Okay. So, let's do a real quick example. Let's say I start here and I walk like 5 meters over here. Okay. Then let's say I go 3 meters here, and then let's say I go 3 meters back, and 5 meters, and now I'm here. Okay, 5, 3, 3, 5. Okay, what was my total path length or my distance? 16 meters, right? Okay, what is my displacement? I am where I started, so my displacement is 0. Okay, my final position, my initial position are the same, so I got 0 displacement. Henry?
If your displacement changed, would it be like the direction, the length, or would it be like the coordinates of the place? Like where would
Yes, the direction matters, and we're going to get to that in just a second. Okay, down at the bottom of your notes, we will get to dealing with the direction of it. Okay? All right, let's talk about speed versus velocity. Here's the speed definition. Okay, now speed and velocity are actually different. Okay, they are not the same thing. When we studied waves, we kind of used them interchangeably. We said, oh, speed, velocity. Okay, and that works for waves, but it doesn't work for kinematics. So we're going to talk about the difference here. First, let's do the symbol. Okay, abbreviating speed, what would make sense? How about just an S? Okay, you know what it's measured in. Write down its units. Okay, just like with waves, meters per second. Okay, and if you skip a couple lines down, you see a place to put average speed. So average speed is change in distance over change in time. Okay, and very simply, let's say we have a car. Let's say it goes somewhere. Let's say we have a timer, we time it. Okay, S equals D over T, easy. Okay, so we might put that equation shortened down there. S equals D over T. Okay, now this is an average speed, so it doesn't mean the object was going that speed the whole time. It just means over the course of that time period, here's its average speed. Could it have been going 0 some of the time? It could. In fact, this one started from rest, okay? So it's an average. Okay, we already talked about that, meters per second. Okay, instantaneous speed. Another definition. That's on the middle of your page on the right. Okay, best way to think about this is simply a speedometer. All right, you're driving along, you look at it, all right, a cop tracks your speed, that would be instantaneous, okay, it's the speed at a given flash in time, okay? So, that's a really easy one. Let's do a little example here, okay? Let's say we're gonna take a road trip from the Pacific Northwest and we're gonna go down to sunny San Diego or Los Angeles, okay? All right, let's calculate an average speed. Just divide it real quick. You don't necessarily have to write this down. Well, let's just do the calculation in miles per hour. Okay, so we do D over T. Divide the two, and we would get an average trip speed of 85 miles per hour. Realistic? How many think realistic? You could do it. How many think, yeah, not really, real world stuff? Oh my goodness. Well, okay, all right, let's talk about this for a second.
Depends on how many highways there are.
Okay, let's say it's one highway, let's say it's interstate. Okay? Maintaining an average speed. All right, now you're gonna need some fuel stops in here. You're going to need at least 2, maybe 3, okay, depending on your vehicle. All right, to stay awake for 13 hours, what else you gonna need? Okay, if it's me, we got Starbucks.
5-hour energy.
5-hour energy. Okay, we got at least 1, 2 coffee stops. The second you cross the Nevada border, you better be getting an In-N-Out burger. Okay, or you are crazy. And then down here, probably another In-N-Out burger. That's like 7 stops. Okay, how fast am I going during the 7 stops?
15.
0 miles per hour during the stops. Okay. Now, what is still rolling while I'm stopped?
Time.
The time's still going by when I'm going 0. Okay, so probably not going to happen. All right, 85 miles per hour, average. Okay, now let's say you did no stops and you just burned through. Could you do it?
Yeah.
Yes, but then you'd have some other kinds of stops, right? Some bad stops where you pay fines and maybe go to jail. Okay, that would involve a lot of speeding. All right, now Utah's up to 80, aren't they? Aren't they up to 80? Okay, you're going to get a lot of Mr. Hicks driving safety lessons in this class. Okay, you just wait. Okay, speed versus velocity. Here's the definition. Okay, how might we abbreviate velocity?
V.
let's do something that makes sense and just call it feet. Okay, there we go. All right, put a unit on there. Okay, still meters per second. All right, now what about the direction piece? Anytime we give a velocity, we have to assign a direction to it. So look up at the top of your page. There are multiple ways to talk about direction. For now, we are mostly going to stick to negative, positive. All right, because we're going to be talking about things that go in a line. Okay, things that go in a line are simple. So we're going to start there. All right, one-dimensional motion. Then we'll get into some crazier stuff with, like, you see angles on there. We might talk north, south, east, west. Okay, what are some other ways of representing directions?
Right, left.
Right, left, up, down, right? Okay. So, an example of a speed. There you go. Okay, how would I make this a velocity?
Give it a direction.
I would add a direction to it. Okay, if the car's going east, I could say that. Another visual for you. Okay, what's the same about these cars?
On the same speed.
Same speed. Okay, what's different?
Different velocity.
Velocities and direction. So same speed, different velocities. All right? Okay, this might help you remember. Let's get some volume here.
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! With both direction and magnitude. Oh yeah!
Okay. All right, what's that guy's name?
Vector.
Vector. Okay, great movie. All right, so down there in the blanks, vectors have both direction and magnitude. We should never forget that now. Okay, direction, easy to understand, self-explanatory. Magnitude just means the value, how big something is or how small something is. So you might put next to magnitude numerical value. It's always a number. Okay, and so with that, let's go ahead and do the little example there. Okay, see if you can work through that and then we'll go over it. Okay, so you got that little number line. Somebody is moving. You're going to give the distance and the displacement. Okay, somebody in this middle back row right here. Okay, what do you guys say? All right, total distance. Okay, what do we got?
100 meters.
Say again.
100 meters.
100 meters, right? Because we got the 70 plus the 30. Okay, good. 100 meters. Okay, now the displacement. What's going on there? Let's go back row, okay? What do you say for that? You notice there's two blanks for the displacement, okay? Give me one of them, okay? 40 meters. That's right. That's the first one. And what do we got to add on that? Anybody? East. 40 meters to the east. Now, part of the time they were going east, part of the time they were going west, but their change in position is to the east. Okay? that's an example of another vector scalar thing. Okay, so let's write down examples of vectors. Okay, so example number 1, displacement. You have to have a direction if you're going to give a displacement. Okay, example number 2. What else is a vector? Starts with a V.
Velocity.
Velocity. Other things we're going to study where direction matters. Acceleration, which we will not get into today. Okay, but that's a vector. It has direction as well. And then in about 3 weeks or so, okay, pushes and pulls. Okay, what's a push or a pull? Okay, forces are vectors. Direction matters for forces. Those are our first 4 vectors we're going to study in this class. Okay, scalars. These quantities do not have direction, only magnitude. Okay, let's put down some scalars. First of all, we got speed and distance. Those are both scalars. They have numerical values, but no directions. Okay, let's hear from you guys. Other things we could quantify where direction is not really a thing.
Oh.
That goes with, okay, give me one.
Length.
Okay, length, good. Length is kind of like distance. It's just another way to say it. Okay, just so you guys know, I'm not saying your names because it's on YouTube. Okay, so I'm just pointing at you. Speed, yes, exactly. Okay, what else? Doesn't have to be a physics thing. Okay, maybe you learned it in chemistry. Okay, what else do you have to like measure or deal with number-wise? Mass, good. That's a scalar. That's a huge one that we're going to deal with. Time, very nice.
Temperature.
Temperature is a scalar. Okay, now it's tricky because temperature, we said that negative and positive is a way of indicating what? Direction. Okay, now with temperature, it does have negatives and positives. We all know that. But do those negatives and positives refer to like physical directions on a map? No. Okay, it's just on a number line. All right, it's a mathematical direction. It's not like a physical direction that you could quantify in space. It's got to be a spatial direction. Okay, so we can have negatives and positives that are scalars. Okay, and there's lots of other ones like, do we say volume? Do we say area? Okay, maybe there's some people that like to bake, all right, like cups and teaspoons and all that. Those are all scalars. You don't say, all right, 2 cups of brown sugar to the north, and then 2 tablespoons of salt south. Okay, you don't say that. Directions don't apply to baking measurements. It'd be weird. Okay? Okay, what else?
Would weight be one?
Weight is a vector because weight is a force. Yeah, that's a tricky one. Okay, we'll talk about that when we get to forces. Yeah, weight is a vector actually. Okay, all right, that's good for today. Okay, we're done. Good intro to kinematics.